Okay, welcome back to the unit on work, energy, and power. In this particular video, I thought I'd show you guys how to calculate the work done on a treadmill or a bicycle, and just to see kind of the applications of that in the real world. So if I look at the treadmill, which is the first one I'll kind of unpack, it's pretty much impossible to calculate work done when the treadmill is flat, purely because if you're trying to determine the work done with your vertical oscillations of the body against gravity, it's kind of hard to estimate what that is. It's much easier to do it once you have an incline, because one of the reasons I've projected this is if you think about yourself running on an incline, that over time, if this wasn't a treadmill and was just kind of a level ground, over time you would continue to move up, and eventually at some time in the future you are a certain vertical distance above where you started, meaning that you've done work against gravity in order to move your body that vertical distance, which makes the calculation of work much simpler. What you'll often find is that this angle over here at which this treadmill is tilted is dependent on the manufacturer of the treadmill, what units they give it in, and sometimes it's given in percent grade and sometimes in inclination. So I'll show you guys how to what does that mean and how to in essence calculate that. So I've just kind of redrawn the treadmill over here, so you can see it's tilted relative to the horizontal, with some kind of angle theta here. That angle can be given as a percent grade or as an inclination angle, right? So what does that mean? Well, if I wanted to calculate the angle, that's just this height over this length. So remember that the sine of an angle is equal to height, opposite over hypotenuse, which is h over l, right? The percent grade, in essence, is the ratio of height relative to the length of the treadmill. It's just this divided by that. So it's just h over l. So you can already see there's a link between these two. It's just the units that they are given in is different. Okay, so the grade, which is the decimal value of the percent grade, is equal to the sine of the angle, which is equal to this ratio of h over l. So for example, if it was a 5% grade, the decimal equivalent of that is just 0.05, right? Which is that would be the ratio of this height relative to the length of the treadmill. But the same thing is if I put the sine of 0.05, I would be able to get, I'll get this ratio over here, and I can convert between the two with the following formula. So the incline angle is just equal to the inverse sine of your percent grade over 100, which is the same as your inverse sine of just the grade, right? That's in essence what I was saying over here. So if I get given if I want to find out what the incline is, equivalent of this 5% grade, I would simply put in the inverse sine of 0.05, and that would give me 2.86 degrees. So if this was 5% grade, it would be the equivalent of 2.86 degrees of inclination. All right. So hopefully that makes some kind of sense. So if I wanted to calculate how much work this person's doing, let's say his mass is 70 kilograms, right? Okay. Let's say that the angle is given in percent grade, so it's a 5% grade, and I'm trying to calculate how much work gets done in a specific period of time. So remember, work is defined as force times distance, right? Okay, so the force in this instance is my body weight that I'm trying to move, and I have to calculate the distance against gravity over which I'm doing that, right? So in essence, that's going to be this height. This distance is going to be the height that I cover at some point in time. So you realize that if I just run for a short period of time, there's not much vertical height that I'm covering. But if I run for like an hour, eventually it'll be like me basically climbing up a small hill, right? So if I need to calculate distance, you can always link it back to your normal speed formula. So speed is distance over time. So distance therefore is equal to speed multiplied by time. Okay, so I need to know what speed am I running on the treadmill. So let's say that my speed is 150 meters per minute. That's kind of like 9 kilometers per hour. It's kind of the same thing equivalent. And the time that I'm running for is 10 minutes. Right? So what's the work that I tend to do over that period of time? Okay, so I have to calculate the total vertical distance that I cover first of all. Well, I'm going to be covering some distance along here, which is equivalent to my speed times time, right? So if I run at 150 meters for every minute that I run, that means in 1 minute I'm going to cover 150 meters. How far will I run in 10 minutes? Well, I'll just multiply that by 10 minutes, and I get 1,500 meters, right? That would be the distance along here that I tend to run. But what's going to be the vertical displacement that I cover in that time? Well, you could use that whole sine formula, and then you can convert this percent grade to some kind of degree, but it's the simple conversion for the vertical distance in that time is just 1,500 meter times the percent grade, where that's given in decimals. In other words, it's 1,500 meters times 0.05, and that's going to give me approximately 75 meters. So in 10 minutes I would have covered 75 meters of vertical displacement. Okay, so that's the distance component. So the work that I do is equal to force. Well, how do I convert my mass into a in essence weight components? So that's simply the 70 kilograms times gravity, which is 9.81 meters per second squared, times the distance that I've covered in that period of time, which is 75 meters, right? And that's going to give me a rather large number of 51,502.5. Now your answer can be in Newton meters or it can be in joules. It's the equivalent thing, so I'm just going to give it in joules to denote the energy. So I would have expended 51,502.5 joules during that time of 10 minutes in displacing my body vertically against gravity a distance of 75 meters. So that, if I divide it by 1,000, I get 51.5 kilojoules. So this might seem a little bit more familiar in terms of energy expenditure, and I can convert that to kilocalories by dividing this number by 4.2. So in other words, 1 kilocalorie is approximately equal to 4.2 kilojoules. And if I do that, let me just double check it, 51.5 divided by 4.2, it's about 12.26. So in other words, this is 12.26 kilocalories. And that's just the energy I expend in terms of moving my body weight vertically 75 meters. Obviously, there's a whole bunch of other factors that I'd need to add to all of this to get the total energy expenditure during that 10-minute interval, but that's kind of beyond the scope of what I'm trying to achieve here right now. So that's just how do you calculate the amount of work done and therefore energy expended in that time period when I'm running at 150 meters per minute, right, for 10 minutes. How does that same example apply to cycling? It's a teeny little bit more complicated. So on a stationary cycle ergometer, I apply force to the crank arm, and then obviously this revolves, and then there's a belt on the inside that covers a certain distance every single time that I revolve around here on the crank arm. So the same principles apply, right? If I want to calculate the work done on a bicycle, it's still force times distance, right? But in this case, the force is not body weight. Remember, body weight on a bike is supported by the seat, so I'm not really even carrying my body weight. It's the resistance that's on the flywheel on the bike itself. So there's a certain amount of resistance. Remember, there's like a knob that you can turn that kind of tightens or increases the resistance. In principle, that's what's working on the mechanics of a bike. So it's a different force value that I have to put in, and the distance that I have to calculate is also slightly different. Remember, I'm not physically moving the bike, but the kind of mechanics on the inside are moving given distances. So if I want to try and unpack this distance component a little bit more, so for every one revolution, the circumference of the wheel will cover 6 meters. So one revolution is equal to 6 meters of distance. Typically, when I cycle, I cover a certain number of revolutions per minute. So if I was cycling at 50 revolutions per minute, I have to multiply that by the distance per revolution. So it's 6 meters per revolution, and I multiply that by the number of minutes that I cycle. So let's make that 10 minutes again. So if I do that, I get 50 times 6 times 10, which is again 3,000 meters. Alright, so that's the distance covered during that period of time. If I try to unpack the force side of things, there's a resistance on the flywheel itself. So let's say that that's 2 kilograms of force. You might sometimes see that the unit's not given in kilograms, it's given in kiloponds. So kiloponds is kind of just the kilograms of force equivalent of that, just somewhat simplified. So there will be a force of, let's say, or a resistance of 2 kilograms. So if I want to calculate the work done, it's equal to this particular resistance, 2 kilograms, times 9.81 meters per second squared, and I multiply that by that distance, and that gives me times 2 times 9.81 58,860, and that's again joules, which is equal to 58.86 kilojoules, which is equal to, if I divide this by 4.2, 14.01 kilocalories. Alright, so in the next video I will introduce you guys to the concepts of power. And remember, what we've shown so far is that work gives us the energy equivalent that I expend in moving a object or resistance or force a given distance. In the next video we'll show what the link is between work done and power. Remember, in the very first video I showed you guys this whole concept of watts. So that's where power really becomes to the fore. So that's what I'll cover in the next video. See you guys there.